Welcome, everybody. It's my pleasure today to introduce Michael Postol, who will tell us about Steenrod squares and data science. Is there a connection?
Okay, so yeah, I'm Mike Postol. I'm work for the MITRE Corporation now. And so I want to talk about, so first of all, I sent in the chat a link to my online book, Algebraic Topology for Data Scientists. So I can make a plug for that. So it's totally free and I can guarantee worth every penny of it. Um, I want to talk a little bit, just to give you some background, sort of how this book came to be, and especially why the latter part of it, things like Steenrod squares, are in a book about topological data analysis. So my PhD back from 1990, University of Minnesota, was very conventional classical homotopy theory, very much pure math. And I ended up not going the academic route, but working for the government. Uh, Primarily, the big things, I did video compression for a while and then error correcting codes for a really long time. And then eventually switched to machine learning for cybersecurity. Uh, and but because my interest in topology, I kind of followed the subject from its beginnings, and actually, was able to use it for some original work looking at Internet of Things devices and how you could classify them just by their internet traffic. So using topological data analysis to take a multivariate time series and turn it into a univariate one. But when especially the idea of persistent homology, where you have this complex that's just growing, um, it made me think of obstruction theory, and I'll talk about what obstruction theory is in a little bit. So yeah, but the idea is if you have a map from a space A to a space Y, and A is a subset of X, could you extend it continuously to a map on all of X? But people around me, I talk about obstruction theory, they'd have no idea what I was talking about. So when COVID happened and we had lockdowns and I find myself with a lot more free time than usual, I decided, okay, I'm going to, relearn all my homotopy theory and settle this question. Uh, and so eventually this book kind of came out of it. I thought, first of all, really give the background. Not everybody who calls themselves a data scientist would have had a class in point set topology or abstract algebra, let alone algebraic topology. And so, you start, if the first page of a paper talks about a quotient group and you don't know what that is, this would give the background for it. And then, try to talk about persistent homology, give a taste for the subject, especially big section on my time series stuff. But what's really sort of has made me curious is, could more advanced algebraic topology, cohomology, homotopy, obstruction theory, Steenrod squares, could they be used somehow for hard data science problems? Given that, they were invented to do harder geometric problems. So as I was, one of the things I did think about maybe publishing this and going through an actual publisher. So, I went through the process, with one just to try it out. And, you get people, you get reviewers, they know who I am, I don't know who they are. So, the first one was, I've never heard of this guy, so no. And then somebody said that they actually had met me, which was sort of interesting. I was curious who. Somebody said, well, he's not well known, but he is known. So I was sort of curious who that was too. But the more serious objection they had is why put all this algebraic topology in a book on data science? Who's ever going to want to read that? It would scare people off. And that really was one of my main purposes in writing this book, is that people with an interest in algebraic topology, maybe this is a way that you could solve some harder, especially classification problems that you might not be able to do otherwise. Maybe your dogs and your cats look so similar to each other that, maybe this would be possible. So that was the idea. And then, of course, there's the other motivation is to be able to put in more math jokes. So, one's like, what do you get when you cross an elephant and an ant? The trivial elephant bundle over the ant. So you can tell you're a true algebraic topologist if you understand that one. But then, there's also the alternate answer is that you get called in front of the ethics board and all your funding gets cut. All right, so let's go through. So again, algebraic topology, and I think we all agree it's a classifier. It was originally made to classify geometric shapes, a lot older than people talking about machine learning. I think we sort of agree homology theory has a use in data science, especially persistent homology. You can get features that then you can throw to your favorite classifier. So this should just be reviewed on the first part of this. But, basically we want to know, is there two spaces X and Y, or is there a continuous function with a continuous inverse? And if so, we say they're homeomorphic. So the idea is you're sort of encoding the geometry into algebra. And if they're homeomorphic, then the algebraic representations are isomorphic. They're the same, but it doesn't really work the other way around. So that's why, you might need more complexity. So questions, especially when you're talking something about Steenrod squares, one thing is they're going to be too much complexity, and the answer is not always, and I'll hopefully make the case for that. This is all for a static case. Are there persistent versions? And the answer is yes, it has been looked at. But could you solve harder classification problems with more complex structures? And is there a practical use? I don't know, but I think it would be interesting to start thinking about some of that. All right, so again, we increase algebraic complexity. A group just has one operation, addition or multiplication. If it's commutative, then it's an abelian group. A ring also has addition, but also a multiplication, and the two are tied by a distributive law. Field has even more. The multiplication's commutative, the non-zero elements all have inverses. Vector spaces have a scalar multiplication. And from where the scalars are a field, if it's a ring and not a field necessarily, it's a module. So vector space is a special case of a module. And the algebra has addition, multiplication, and scalar multiplication. All right, so when we do algebraic topology, we go up in complexity too. So homology, the main idea, you've got endpoints and they're convex hulls and n simplex. So like 0 simplex is a point, 1 is a line segment, 2 simplex is a triangle, 3 is a tetrahedron, and so on. You stick these together, then you get a simplicial complex as long as all its faces, any simplex, all its faces are in the complex, and any two intersect on an entire face. All right, and then formal sums of these, you get P chains, and then you have this special boundary homomorphism that, and if you, so the P cycles are the kernel of the boundary homomorphism. The P boundaries are the image. And if you apply the boundary homomorphism twice, you get 0. So the boundaries are contained in the cycles. And then I'll do what I just complained about and say the homology group is the quotient group. So that's why I put in my book, what is a quotient group? All right, so the problem that you would need this for, a line to plane are not homeomorphic. It's very easy to tell why. You just pull out a point. the line becomes disconnected, but the point, if you remove a point from a plane, it's still connected. But what about R2 and R3? That wouldn't work, but Rn is really an n sphere with 1 point removed. So here's the stereographic projection, shows the example for a 2-sphere in a plane that you match up every point except the North Pole by taking a point, cutting through the sphere, and wherever you hit the plane is the point that you match it up to. And you'll get the entire plane, but not the North Pole doesn't match, so that's like a point at infinity. So homology, because homology of a sphere is 0 unless it's dimension 0 or n, that's going to show that R2, R2 and R3 are not the same thing. All right, so cohomology now. So that's sort of homology backwards. The maps go up in dimension. And the way you get it, so instead of chains, you talk about cochains, which are homomorphisms from a chain group to some other group. And you're usually going to make this actually a ring. In topological data analysis, usually it's Z2. It'll be the integers, in a more traditional algebraic topology class. And if you have a cochain F, then you can define a co-boundary map. So if you're in C plus P plus 1, if you're on P plus 1 cochains, you want to take a P plus 1 dimensional simplex and take that to this group. So the way to do it then is, because you have the boundary, you do the boundary first, and then you have this map F that going to G. So that's a co-boundary. And then very analogously, you could get cocycles, co-boundaries, cohomology groups by just, the kernel, the image, and the quotient. All right, and now here's the bad news, right, is cohomology groups can be computed from homology groups and vice versa using the universal coefficient theorem. It's really very easy. And if X and Y have the same homology groups, they have the same cohomology groups. So why would you do something like this? And because the real power is that it also has a ring structure, the multiplication being called a cup product. So the cup product of two cochains, CP and CQ, and we write it with like this cup shape, so that's why it's the cup product. But pretty much you take, if you want that to do something to a, so first of all, we have to use a ring now, so we need a multiplication. But if we've got a P plus Q simplex, what we'll do is we'll take the first P plus 1 points, and we know that CP is a cochain, so it can do on P dimensions, so it knows where to take that. You take from VP up to VP plus Q, apply CQ to it, that knows what to do, and then you just multiply it because their images are inside of a ring. And then this is the co-boundary formula, and that basically shows you that cycle any two cocycles, so the co-boundary of it is going to be 0, and so the product of two cocycles is also a cocycle. And the cohomology class of cup products depends only on the classes of CP and CQ. So those are going to form a ring, the cohomology classes, and we can talk about that, a cohomology ring. So here's an example where cohomology works and homology doesn't. All right, so just again, Sn is going to be all the points in Rn plus 1 whose norm is 1. So S1 is a circle, S2 is a hollow sphere. If X and Y are spaces, then their Cartesian product, X cross Y, is the ordered pairs X comma Y. But it's like putting a copy of Y at every point. From 0 to 1, S1 cross I is going to be putting a line segment every point of the circle. S1 cross S1, you're putting a circle at every point of a circle, you get a torus, hollow donut. And also, for example, we'll talk about the wedge product, X wedge Y, which is just the 1 point union of X and Y. So for example, 2 circles is just going to be a figure 8. All right, so let's say, after this talk, you're getting really hungry. It's around lunchtime, so you want to go buy yourself a donut. And you go to the donut shop, and instead of that, they give you something like what's on the right. Actually, you can think of it more of just a sphere with 2 circles attached, and by a single point. So yeah, the store owner says, well, it's the same as the donut. If you look at the homology and the cohomology groups, they're actually exactly the same. So, is he right? Is this, is a sphere with 2 circles attached the same as a donut? Hopefully not. So it turns out the cohomology ring of this thing is actually trivial. And the reason is the 2 things you might be able to multiply, the 2 one-dimensional cycles, are not really the boundary of anything. These 2 circles aren't the boundary of something. So their product is going to be 0. Whereas in the torus, you have 2 one cycles are pretty much going around the circle, the long way or going around the short way, and their product is going to be the 2-dimensional cohomology class of the donut, the non-zero one. So the cohomology rings don't coincide, and so these are actually different. All right, what about usefulness? Can you use cohomology for data science? Yeah, first of all, now TDA uses persistent homology, so is there a cohomology analog? And yeah, and there are various versions. I mentioned Aubrey HB's thesis from 2001 because it also gives the main topic is a persistent description of Steenrod squares. But RIPs are which is a fast algorithm for computing persistent homology, very popular now. That really depended on cohomology. And you transpose the matrices to convert from homology to cohomology, and it actually speeds up the computation a lot. So so this was useful for that. It's also sheaf cohomology, which is something I've been learning a lot more about lately. That could be used for sensor fusion applications to detect incompatible sensors. So if you're measuring the same thing, but in very different ways, sheaves can be a way to fuse them all, and the cohomology is a way of telling, okay, well, these things can't be fused. All right, so question though is, what about something more advanced? What about homotopy theory? What about Steenrod squares? Could they be useful for solving hard data science problems? And I don't fully know the answer, but there's a lot of hints that 1, this might be possible, and 2, because of the classical uses, that would be something to think about. All right, so what's a Steenrod square? Oh, and I should mention that Steenrod is actually my advisor's advisor's advisor, so sort of my mathematical great-grandfather. Besides Allenberg and Steenrod having the standard axioms that define what's a homology theory, what's a cohomology theory. So Steenrod squares are going to change things actually into an algebra over an algebra. They're much more complicated algebraic structure. And what they do is they act on cohomology ring with coefficients in Z2, which is nice. Again, in topological data analysis, we usually do things over Z2 anyway. And they provide maps. So what SQI does is it takes a Pth cohomology group and maps it to the P plus I cohomology group. Of course, you only do this from 0 up to P. It's 0 otherwise. But at SQ0 is the identity, and SQP is going to be the cup product. So SQP of alpha is the cup product of alpha with itself. So that's where the name Steenrod square comes from. It's not like a 4-sided square, but it's something times itself. Okay, you can also do this with odd primes too, if you really like those better. those are called reduced powers, and the formulas, as bad as these are, a lot worse. So I would, once Steenrod squares become really useful and comfortable, that would be another thing to look at later. Okay, so why would we care about Steenrod squares? So first of all, and again, as Steenrod himself said, you're encoding more of the geometry into algebra. It's also closely tied to the extension problem, which I still think might have something to do with persistence. And it already is used as a classifier. You have, if you look, it's Milner and Stashev's book on characteristic classes. And I think it actually even has some physics applications, but I don't really know what they are. I think some things to do with string theory and but they use a shape called a vector bundle. And I talked about vector bundles and fiber bundles and all that in my paper, so that's something to look at. But it's used to classify those shapes already, so it already is used as a classifier. And then if you look at the Gonzalez-Diaz Real papers, there are explicit formulas for computing Steenrod squares. Now you do have an issue with complexity, but that is manageable for SQI if I is small. And remember, SQI can only push you up as high a dimension as the thing you're starting with. So if you're dealing with things in low dimension, it's not necessarily going to be that bad. And SQ1 for sure isn't going to be that bad. So I'll get into what the relationship is. All right, I apologize for this. This is really, really ugly. But you could use this as a definition for Steenrod squares. This is all the properties. There's also more explicit construction of it. But there's things I want you to think about. First of all, is that all the commutativity properties, functor properties, all the things that homology and cohomology have, Steenrod squares also do. So if you're, if you have a continuous function from one thing to another, these, you get these cohomology operations. I also use K and L. Would be like a subcomplexes case. So it's a little more general. But the things I really want you to look at are these last two, the Cartan formula and the atom relations. So it's saying, first of all, is you could apply a square to, so I'm using X times Y as the cup product because X and Y are cohomology classes. And those actually have formulas. Whether they're nice or not, I don't know, but I go through a few of these manually in the book so you can see some examples. And then the atom relations are, so you have a multiplication of Steenrod squares, which is really going to be by composition. And the atom relations tell you, okay, well, composition, this is a way to define it. But there's a formula for it. And so that means what you really have, and if you think of this SQIs as a scalar multiplication, then you have an algebra over an algebra. So the scalar, what would be the scalars are elements of an algebra themselves. All right, so Steenrod originally came up and he was looking at things like extension problems and classification. He came up with something called a cup biproduct, which is much easier to define than what modern day Steenrod squares. It's also horrible to try to prove things with them. But basically the idea behind cup biproduct is, remember, a cup product, you have something, it's going, and we're so for a cup byproduct, we're going to overlap. Now, this actually should be, there's a mistake, it should be P plus Q minus I. So it's not the full P plus Q plus 1. but here you can see it. So we take the first P and the last Q overlap, and that's what a cup-I product is. So SQ of I is, and I'm putting the U cup I of U is going to be a map from HP to H2P minus 1, minus I. And in modern day notation, you have SQ up I is SQ down P minus I. Extension problem, and that's going to be our example of a problem we could solve with Steenrod's now with cohomology. All right, so, and I'm going to talk about cells instead of simplices. So cells are squishy simplices. Yeah, so you work with, a line segment, which, you can bend, you take as a 2-cell and so on. And I won't rigorously define a CW complex, but the idea is that the cells are attached to lower dimensional cells. So Bn plus 1, which is Sn along with the interior, is an N. And that's going to be, so an N cell is a copy of Bn attached to a finite collection of lower dimensional cells. So if F and G are continuous, we say they're homotopic if there's a function from X cross I to Y, big F, so that big F of X and 0 is F and big F of X and so these are, so you can kind of continue. And homotope is an equivalence relation. So if X is actually a sphere Sn, then we have a special name for the classes of maps from Sn to Y that's called pi. All right, so so our example pi1 of Y is the fundamental group. It consists of loops starting and ending at some point Y0, because what you're doing is you're sort of mapping a circle to a Y. So it's a set of all the loops going from, starting at Y0 and coming back there. So they have a natural multiplication, which is, you go around one loop and then you go around the other loop. And the 0 element is the loop where you start at Y0, end at Y0, but don't go anywhere else. It's sort of the constant loop. And with n bigger than 1, they're analogous homotopy groups. So here's the idea now is we're going to, the extension problem, we're going to have a subset A of X, and we have a continuous function H going from A to Y. So we want to know, is there a continuous function F going from X to Y so that F agrees with H on A? So F of A is equal to H of A for A and A. So letting G be the inclusion, okay, which is just taking things in A to itself, what we want to do is find an F going from X to Y so that F composed with G equals H. So G goes from A to X, and we want a function to go to Y, which will be the same as H, which is going from G to Y. Okay, so here's the map. Here's a little diagram of that. Okay. Now, homology, if we have these continuous functions, these turn into chain maps on homology. And I'm just going to replace AX and Y with HQ of AX and Y. So those are the homology groups. Now these are going to be, the stars are going to be group homomorphisms. All right, so here's our example. Why would you think you could do this and why would you think you couldn't? And that's really going to form the basis of what obstruction theory is. Okay, so these two examples are really important. First one is a constant, okay? If H of A is equal to Y0 no matter what, then we could extend that to all of X by just letting F of X be Y0. Okay, so that's the easy case. Now if A is Sn and X is Bn plus 1, so X is pretty much A's interior, well, A with its interior, I should say, then, and let Y equal Sn, all right? So we have a map from Sn to Sn, which is just going to be the identity. And we want to know, can we extend it to the, so let's say, a circle, can we extend it to the entire circle? All right, well, here's the problem is that a ball circle, yeah, that's in homotopy theory, it looks, or homology theory, it just looks like a point. So for p bigger than 0, HP of x is going to be 0. So what you're trying to do is, so h star is going to be the identity. Okay, if you have an identity function, h star is the identity. But g star has to be 0 because when you're going from the homology of A to the homology of X, which is always 0, so that means that G is going to be 0. And that means F star G star also has to be 0, and that can't be H star because which is the identity. So we can't extend H. Okay, so those are the two prime examples. Here's something you can extend is like a constant. Something you can't extend would be like the identity on the boundary part of a circle, which you can't extend to the inside. And that's the prototype for anything else we would look at. All right, so obstruction theory. All right, I now I have this cell complex. I'm looking at I've got a map from A to Y, and I want to extend up to X minus A. So what I'm going to do is I'm going to go one dimension at a time, all right, and do it kind of inductively. So let's say I've extended this to the n cells. So what means that, so for any n plus 1 cell, we already have a map from its boundary to the cell Y. Sorry, from the boundary of n plus 1 cell, which has to be cells that are n or lower, we have a map from that to Y. Okay, so that's good. So, but this now being a map from Sn to Y, the boundary of, Bn plus 1 is going to be Sn. Okay, so that's an element of pi n of Y. And so we can do it if it looks like a constant, which means that it's going to be the 0 element of pi n of Y. So what you do is you kind of get a cochain group then. You're basically the maps from X to Y, or I'm sorry, from X to pi n of Y. So you're taking, again, you're taking an n plus 1 cell of X, you're taking its boundary, which looks like Sn, and you have a map from that to Y. So that's like taking a map from X to the nth homotopy group of Y. So that's called the obstruction cochain. If it's 0, we're like the first case and we can extend it. If it's not 0, then we have problems. So that's kind of how obstruction theory works. And something I thought about is maybe in persistent homology, we might want to extend this to an interesting function. Maybe we have an interesting function that in an earlier stage of the filtration, but maybe there's an obstruction and maybe that'll just tell you something more. So one thing I was looking at, well, you can't really take homotopy groups of anything but spheres, and that's bad enough. But I was thinking maybe image or maybe video compression, because the grayscale and 2 chrominance values for every pixel are going to be kind of like a point in S2 and a 2 sphere by just normalizing their values. So that's possible. Maybe that would be a possible interesting case of this. All right, so here's sort of the motivation. Now, Steenrod gave this 1957 colloquium lecture, and I'd really recommend it. It was published posthumously in 1972, but it was a lecture he gave at Penn State. It's very dated, but it really gives a lot of what his thought process was for inventing Steenrod squares. And now if we're going to take this extension problem, and now we're turning this into That's just supposed to be an F star. I don't know what that is next to it. But so when you do cohomology, arrows all go backwards. So we get a diagram kind of like this. And we want to find an F star now so that H star is G star F star. Okay. But now these are ring homomorphisms, so they're going to preserve cup products. We can even do better than that, and by defining a cohomology operation. So cohomology operations and Steenrod squares are an example by all those ugly properties I put up there. They're going to go from HQ of X to HR of X. And if we have a map from X to Y, they're going to commute in kind of the way you'd like. So F star of TY is TX of F star of U. Okay, so if U is an HQ, it doesn't matter if you use F star, take that to HQ of X, and then go up to HR of X, or if you go to Y for, or if you go up to HR of Y and then go back to X. Okay, that'll work out. So not only does the solution of the extension problem have to be a ring homomorphism, but it's got to commute with all the cohomology operations, including Steenrod squares. So one more thing I have to define to show this example. So in an n-sphere, we have a projective space Pn, which is what you do is you identify all the antipodal point of x and minus x of the sphere Sn. So P2 is not only called the real projective plane, also called Boy's surface. You could also make one of these by taking a strip of paper, twisting one end like a Mobius strip, but then twisting the top end also. And here's like a three-dimensional projection of this thing. So kind of scary looking. All right, so, but anyway, and you can look in my book for a proof, but Pn turns out to have one cell in every dimension from 0 up to n. So we're going to look at a special case of the extension problem called the retraction problem. Okay, and a retraction of x onto A. So A is a subset of x. That's a continuous map f going from x to A, so that f of A equals A for every A in A. And then A is called a retract. So it's kind of like the extension problem, but A and Y in this case are the same thing. All right, so let's let X be P5 and the 5-dimensional projective plane, but I'm going to come along and tear out the 1 and the 2 cells. So we're going to those are going to be kind of collapsed to a point. And A is going to be the image of P4 under that. So that's going to have lost its 1 and 2 cells also. So let's say F going from X to A was a retract, and G from A to X was inclusion. So G star F star is the identity. And HQ of X, this turns out to have to be of the form the image of F star plus the kernel of G star. All right, so and also G star is actually an isomorphism going from the image of F star to HQ. So because you really, I mean, basically because you got to get the identity when you're composing it with F. So that's got to be an isomorphism. So what happens is then the image of F star is a subring and the kernel of G star is an ideal. And the cohomology of A and X with Z2 coefficients. So I'll just show those in the table. And these are Z2, so there's only going to be one class that's non-zero for all of these. All right, so now we know that G star is going to be an isomorphism in dimensions less than 5. And the image of F star is 0 in dimension 5, just because you're starting from 0. So the image of F star, first of all, if this is going to be a retraction, it has to be a subring. And this is actually true because the smallest dimension where it isn't 0 is 3. If U is the non-zero element and we cup it with itself, then that's going to be dimension at least 6, and that has to be 0. So you don't have to worry about closure in this case. it really is going to be a subring. So I was hoping it wouldn't be, so that cohomology could settle the question. No, you can't do a retraction, but it doesn't really settle it at all. But now let's look at Steenrod squares. So the Steenrod square, SQ2 going from H3 to H5, if we take the non-zero element of H3, call that U, SQ2 of U is the non-zero element of H5. Now the image of F star contains U, but is 0 in dimension 5. Okay, remember F star is going from A, and when A is 0 in dimension 5, so the image of F star has to be 0 in dimension 5. So what happens is if you take the non-zero element V in H3, we've said that F star of V is U. So F star of SQ2 of V, though, is going to be F star of 0, which is 0, just 0. So SQ2 of U is non-zero, but SQ2 of F star of V, which would be U in this case, would be 0. And so that's a contradiction. So that means the retraction can't possibly exist. But without Steenrod squares, we would have never known that. All right, so just to go through real quick, I'm getting close to my time here. So some other issues, again, I didn't mention persistence, but again, I would refer you to Aubrey HB's thesis. Complexity, okay, it could be absolutely miserable. You are talking exponential, but so they did it for simplicial sets, which are kind of a generalization of simplicial complexes. But if you have a cochain in C I plus K of X of Z2, the number of terms in the formula for SQI is going to be in the order of I to the K plus 1. So is this really bad? Maybe, but what if I is small, it won't be so bad. Like, for example, if C is dimension 3, the worst that I could be is 3, and 3 cubed is 27. So you have 27 terms per simplex. And the terms are face operators, which are where you remove a vertex from a simplex with an ordered set of vertices. So this isn't so bad. And the lower dimension, you start with the fewer Steenrod squares. Now this would look a little funny if I is equal to 1, but in the HB thesis, it's actually there's actually a simplified formula for it. Okay, so to conclude,
Can I maybe interrupt you here?
Excuse me?
Sorry. Can I interrupt you here? Because we have a question in the chat.
Okay.
Namely, can the concepts related to Steenrod squares be used in clustering, as in AI, machine learning, data science? Any high-level overview would be useful.
Okay, that I'm not sure. I haven't really thought about that. But yeah, it'd be an interesting thing to think about. You know, I've sort of been thinking classification just because, you know, that's topology does, but yeah, that would be a question. Yeah, so that's pretty much all I have is that yeah, it's a very open research area, but I believe it's possible, and I think eventually it'll be shown to be useful.
Thank you.
Okay, anything else?
I don't think so. Thank you.
Okay.
Oh, Teresa, I think he's at the end of his talk, not the end of the question. Oh, and you're muted, Teresa.
Sorry, I didn't understand that you're already at the end of the talk. Okay, thank you. Then let's please all unmute ourselves.
Some of the references for the YouTube, but
oh, I think let's first just unmute ourselves to clap together.
Okay,
And let's start with this
question.
Yeah, thank you.
Okay, that's my contact. Okay, yeah, so was there any other questions?
Yeah, please, let's open for questions. maybe while people are thinking for questions, I wanted to ask, you said sometimes that this is written in HB's thesis. Who is HB?
Yeah. Oh, so she has a hyphenated name. I forget what it is, but she professionally just made it into HB. So it's
Oh, okay.
Aubrey HB. Yeah, it's a little hard to do a citation, but
Okay, but that now together with persistent cohomology operations, it's easier
yeah,
to Google. Thank you.
yeah, I can look that up.
Yeah, I have a
yes.
couple of comments and questions.
Okay.
So I think I wrote Michael yesterday about this, and I was maybe hoping some of those references will be included as well. But I don't think the research presented, although I share the appreciation for the goal, it's not state of the art. I think, as you pointed out, for example, Gonzalez, Diaz, and Real have a method to compute Steenrod squares that is exponential. But the state of the art is actually much better. It's quadratic on the length of the representative cocycle. And that has actually made the computation of Steenrod squares much, much faster, and has allowed for the incorporation of this invariance into the persistent pipeline. There are so-called Steenrod barcodes now. And those Steenrod barcodes can be computed effectively using these new formulas, and they have already been implemented on software that is freely available. The software, I think it's called Steenroder. Actually, I'm sure it's called Steenroder. And it has been used also with real-world data for classification problems that are non-trivial, particularly.
You mentioned the chemical example, or?
That's right. So in particular, a data set that we topologists like a lot, the conformation space of the cyclooctane molecule. It's an example where one can detect finer structures because of the presence of these Steenrod barcodes. Yeah, so I do think that what you're pointing out as a research direction has been pursued, and there are a lot of developments that have come after the cutoff that you're presenting.
Yeah, and I think that that's really good news. It was definitely not something I knew about when I was writing the paper. So yeah, I got your list of references, so thank you for that.
Great. Any other question? Yeah, we have one question in the chat, but it's pretty long. I'm not sure if this is maybe better something to do via email. It doesn't really seem to be a question, more like a, could you please validate the following? So I'm maybe won't read the whole question, at least not for the recorded part. Yeah, so any other questions maybe? Okay, if not, we can also close the recorded part here, and then people can still ask questions offline. Thank you again very much for your talk.
Okay, thank you.